So metals, metals have loosely held electrons or tightly held electrons? Loosely held electrons. That's one of the characteristics. We can excite the metals easily in a flame. So if I excite the metal electrons here in the flame, excite means they're going to get more energy, and they'll go to higher energy. They don't stay excited forever. Do you know what's going to happen? They're going to cool down. When they cool down, they radiate electromagnetic radiation. So for example, here, when I heat the metal up, do you know what I don't see anything, but I can feel something. Do you know what I feel? Heat, yeah. And that heat is actually electromagnetic radiation. That heat that I feel is infrared. And what I'm doing here is I'm exciting the electrons using the flame, and the electrons get excited, higher energy, and then eventually they'll drop back down to lower energy. When they drop back down, energy is conserved, first law of thermodynamics, and so that energy has to be emitted. And in this case, it's going to be emitted as light or heat, infrared light. That infrared light strikes your hands. What does infrared energy do to matter? Vibrate. So your hands, the atoms in your hand will start vibrating more, the molecules in your hand. You don't want the atoms in your hand vibrating too much, because if they vibrate too much, it disrupts or breaks the structure of the proteins. You know, these proteins have complicated structures. They got to maintain that structure. So it does something called denaturizing proteins. But what happens if I heat this up more? It'll melt. Well, stainless has a very high melting point. Eventually it's going to melt. But before it melts, it'll start to change color. It'll start to glow. And when it starts to glow, you can see the light. It's going to be visible. Do you see it glowing? Mm-hmm. What color is it glowing? Kind of red, yellow. Do you see that? If I keep heating this up, and hopefully it doesn't melt, but if I keep heating this up, eventually it will glow what color? White hot, yeah. And white hot is, okay, so both, I see infrared, I see it glowing. It stopped glowing, but it's still radiating infrared heat. You know? But eventually it should start glowing white hot. And so what we could do is we could make a light bulb out of that. So let's take a look at light bulbs now. Incandescent light bulbs, right? And so if you look at the incandescent light bulb, they use metal. I use stainless steel. Why did I use stainless steel? One, it has a high melting point, and two, it's difficult to oxidize stainless steel. You know, if I use some other metals, when I heat it up here, it's going to create an oxide coating like a penny. If I use copper, would copper last very long? No, it's going to turn brown, and then it's going to turn black. And that coating is copper 1 oxide or copper 2 oxide that doesn't conduct electricity. The electrons aren't loosely held there. We need something with loosely held electrons. And so in a light bulb, stainless steel isn't used. Do you know what's used in an incandescent light bulb? Tungsten. Why tungsten?
Because of its properties.
Yeah.
It's like steel, but it's more.
Yeah, tungsten has a very high melting point. And so you could get this glowing white hot, really white hot, and it doesn't melt. Other things you get glowing white hot and then it starts to melt. It'll melt even before it gets white hot. And so something like this, tungsten, and rather than using a flame to excite the electrons, you know what we're going to do? We're just going to plug this in to a power source. And so we need some kind of electrical power here. Oh. You mean like this?
Electrical. No, this. Oh, yeah.
Um,
Because he just burned. Oh.
like battery power.
Yeah, the battery.
Like,
Alright. We could do that.
I missed it.
But anyway, so if I have this, what I'm going to do is I'm going to excite the electrons. Electrons actually, how do I excite the electron? Well, you're creating a flow of electrons called current. This current of electrons, it doesn't pass through smoothly through there because, you know, at room temperature, are the tungsten atoms fixed in position or are they vibrating at room temperature? They're vibrating. And so you got tungsten atoms vibrating, and then you have these electrons trying to make their way through the tungsten. And what's going to happen are those vibrations are going to cause it to deflect, whatever, or change paths. And we call that resistance. And so as electrons move through here, it's going to meet some resistance, and eventually it's going to heat up. Things are going to get hot due to that resistance. As it gets hot, then it'll start to glow. So initially it'll glow red hot, and then what? And so we have red. And what's higher in energy than red? Orange, yellow. Yeah, and then once it emits all colors of the rainbow, when something emits all colors of the rainbow, it looks white. Because all the colors add up to white. If it looks black, then do you know what's happening with black objects?
Absorbing all the.
It's absorbing all the colors of the rainbow. And so if something, you know, transmits, emits, or reflects all the colors, it's going to appear white. If something absorbs all the colors of the rainbow, then it's black. And how do we form all the colors? Well, all the colors, this is going to come from this. Let's say normally the electrons in tungsten are down here at this lower energy. When we excite the electrons, they get excited to higher energies. And so we'll have energy as the y-axis here. And so we excite it a little bit. It doesn't stay excited forever. So eventually that electron is going to drop down in energy and it's going to emit light. And the light in this case would be infrared. Now infrared has, would you say, longer wavelength or shorter wavelength than visible?
Longer?
It has longer wavelength, lower energy, lower frequency. And so this would be infrared. And you can feel that as heat. Now, if we excite the electron a little higher in energy, we'll go into the visible. The first color we encounter in the visible is red. And so red light is going to have a shorter wavelength, a higher frequency, and higher energy. And so this would be red there. And then what's higher in energy than red? Orange. And so we'll start emitting orange light here, and then higher. So we'll go yellow. So we'll get orange, then yellow. And so red, orange, yellow. What's next? Green. And then blue, indigo, and violet. And then ultraviolet, right. And so what we do is we'll just excite the electron to higher and higher energies, and then when it drops back down, it'll emit higher and higher energies of light here up through ultraviolet, and including eventually we could get from ultraviolet to X-rays and gamma rays in theory. X-rays, I used to work with X-rays. We had only a tungsten element here, not tungsten, copper. We excite certain electrons in the copper and it starts to emit X-rays. But here, and what we call this is a continuous spectrum. When you take all the colors of visible light and you combine them, we get white light. And so if we just heated this up a little bit, then it's just red or red-orange, yellow. But if we continue heating this hotter and hotter, then we should emit all these. And we have
Why
white.
don't you see green when you heat something up?
Because when red, orange, yellow, and green combine, it doesn't make green, you know. In other words, there's still red, orange, and yellow there. And so when the green combines with that, it doesn't look green. Whereas red, orange, yellow kind of all have the same kind of shade. The green's going to shift it more to the white, you know, as we go up. And then the blue, we don't see blue, but it shifts it more blue. Indigo, violet. And then eventually it's just going to go to white, basically. That's what it does. All right, so we just got to, you know, adjust the power. We got to make sure there's enough power that we get not red light, but we get white light from this light bulb. Okay. So we measure this using what we call a visible spectrometer. I think you go to ultraviolet too. Hopefully we don't get too much ultraviolet from this. But for certain light bulbs, they do emit some ultraviolet. You got to be careful about. What we want to see is we want to make sure we don't get too much ultraviolet. And so one way to do that is we can look at the spectrum, and we have something called the visible spectrum. And we measure this using a spectrometer, a visible spectrometer. And let's plot it out. Over here we have infrared, and then red, orange, yellow, green, blue, indigo, violet, ultraviolet. Here. The spectrum usually plots things out in terms of wavelength. And so over here, or energy. In this case, this is in terms of energy. And so we have increasing energy as we go left to right. But when we increase the energy, we decrease the wavelength, which increases the frequency. And so we have increasing energy, increasing frequency, decreasing wavelength. And so at the border between infrared and red, we have a wavelength of 760 nanometers. It's very small. At the border between violet and ultraviolet, we have a wavelength of 390 nanometers. And so the visible spectrum ranges from about 800 nanometers to about 400 nanometers. And so if we're going from about 800 to 400, then green is kind of in the middle of this, which is around 600 nanometers. So green would be around 600. And around 700, we have orange, yellow. And then around 500, we have blue, indigo. You see that? How we can divide the spectrum. And so this is just qualitative, we estimated. And so some light bulbs give off light that looks similar. You know, all these light bulbs are going to have some infrared. You don't want too much infrared. Because if you get a lot of infrared in a light bulb, you're generating a lot of heat, but you aren't generating any visible light. And so you're just wasting a lot of energy. And so we like to minimize the amount of heat that's generated infrared. You want a lot of red, you want a lot of orange, you want a lot of all these colors, and you don't want much UV. So hopefully the spectrum looks like this, a big hump. And this hump will show us the intensity of the light.
That's the negative cosine.
Something like this. But, you know, it depends on the light. Some people want more red, orange, yellow. You know, they call these the warmer colors. Whereas these are the blue, indigo, violet would be the colder colors. And so some light bulbs will bias the lower energy here and reduce the higher energy. Other light bulbs you want as white of light as possible, so they'll have a more even distribution of intensity in here. So it depends. A lot of people want light bulbs that mimic the sun the solar spectrum. Sodium lamps. Sodium lamps, like the sodium lamps are hard. I mean, if you were to read using a sodium lamp, it'd be difficult because sodium lamps, do you know what color they? Orange, yeah. So if you like orange light, then it's good. Sodium lamps are good. I don't want a sodium lamp. You know what I want? I want a hydrogen lamp. Why do I want a hydrogen lamp? Because the sun is made up mainly of hydrogen. And so a hydrogen lamp should be fine. It's not that difficult. You can make an air lamp. You know an air lamp? An air lamp would be like a lightning bolt through the air. That would be an air lamp. And that produces, a lightning bolt produces white light, right? But it would be hard to read using a lightning bolt. And so what we have to do is we have to control it. And so what we're going to do is we're going to generate a lightning bolt through hydrogen. How do you generate a lightning bolt through hydrogen?
The tube with hydrogen in it and a cathode.
Yeah, right. So what we're going to do is we're going to hook this up and create a voltage, a high voltage, so that we can generate some kind of lightning bolt here. But a typical lightning bolt, let's say this is positive here, this is negative here. Then we have electrons that want to go from the negative to the positive, but in a typical lightning bolt, it's pretty jagged. It's pretty jagged because even though gas is empty space, mostly empty space, there are other atoms and molecules and whatnot in here. If there are a lot of atoms in here, then it's going to have a jagged path because there's going to be a lot of collisions. And so what we want here inside is a low pressure gas. If we have a low pressure gas, then we'll get a much nicer, what we call electric discharge or lightning bolt.
Why is it low pressure?
Low pressure so there are fewer collisions. So the electrons, you want them to travel a straight path.
It's just smooth out there, huh?
Yeah, otherwise it'd be arcing like this, zigzagged everywhere, like a lightning bolt. And so with low pressure, the other reason we want a low pressure gas is because we could use a little lower voltage. So rather than like, let's say 15,000 volts, we could have like 5,000 volts. And so we'll just have a low pressure. And then we're going to put in hydrogen gas in here. Okay, when we have hydrogen gas in a discharge tube like this, there's energy there, and the energy can break the molecules apart. They like to stay together paired like this, but they can be broken apart into atoms of hydrogen. So this would be atomic hydrogen. What's that?
If there's a leak, can it explode?
Yeah. If there's a leak, then it can explode with oxygen. Fortunately, there are no leaks here.
Is that a hydrogen lamp?
Yeah, this is a hydrogen lamp. Yeah. So I have a tube that's filled with hydrogen gas. Yeah. And I have a piece of metal this is in glass. So there's a piece of metal up here. You can't see it. And another piece of metal down here. And we put a high voltage, like 5,000 volts. This is actually less than 5. But I think this is about 1,500 volts. I don't want to break it. This is low pressure, so it's a vacuum. Low pressure just means it's lower than atmospheric, so it'll implode. I don't want it to implode. This is not any glass. This is a special glass. This is called quartz glass. And with quartz glass is pure SiO2. SiO2, silicon 4 oxide or silicon dioxide. And if sodium gets into the structure, then it makes a different kind of glass, or it can do something called devitrify. That is, it can lose its glass state. Vitreous is glass. devitrification of glass is a problem. And that is I have sodium on my hand, so if sodium ions gets in there, then it forms a ceramic, mineral type thing and gets brittle and breaks. And so to prevent that, I'm going to wipe any sodium. The sodium just doesn't go in there. It has to be hot. So sodium from electrolytes. We all need electrolytes. Everything you touch, you leave sodium on. Did you know that? Yeah.
You mean like oils?
Yeah, your oils, your perspiration when you sweat. I don't know if sweat has. Let's say you have some sweat dripping down, and you taste a little bit of sweat. It tastes salty, right? So the sodium and electrolytes. So that's a problem because since everything you touch will leave a residue of sodium, then you have to be very careful about contaminating things with sodium. And so contamination is a big problem in chemistry. We always worry about cross-contamination things.
Not if you automate stuff.
Yeah, that's true. If you just use a robotic arm instead, a robotic arm, I could just pull that off. Wouldn't leave sodium residue, most likely. All right, so we're going to make a lamp. And hydrogen, each one consists of one proton and one electron. And so that electron in there, based on physics, this is what we call classical physics. When we look at the H atom, we should be able to excite this electron. So we can excite it different ways. There could be collisions between the H atoms. There are going to be electrons being knocked off of this current, other things. And so we can excite this electron. So in terms of energy levels, let's say normally the electron resides here, but maybe the electron's moving a little faster. So if it's moving a little faster, it'll get further away from the nucleus. And so we can excite it here and here and here. So we can excite the electron to higher and higher energies.
Oh, and when it drops in the energy, it releases a photon.
Right. So when it drops, it's not going to stay excited forever. So let's say an electron gets excited to here, it's going to drop in energy and emit light. We don't have to excite it with light. It could be excited with light, but we can easily excite it with light. But in this case, we're using electric power to excite the electron. If the electron gets all the way excited up to here, it'll drop and will emit higher energy light, higher and higher energies of light. This way. And so the classical physicists, they would visualize the electron as orbiting the nucleus like the Earth, orbits around the sun. So we get an electron like this, or satellites orbit the Earth. And those orbits can change. So let's say the satellite goes to a little further orbit. It's got to have a little bit more speed, a little bit more energy, so it can orbit further and further away. And so our hydrogen lamp should emit white light, because as long as we put enough power in there to excite things, maybe it will start to glow red hot first, and then orange, yellow, and eventually it should glow white hot. That's what classical physics predicted. Classical physics predicts that our hydrogen lamp should glow white hot, like the sun. It's not exactly going to be the same as the sun, because the sun's much hotter, but it should essentially do the same kind of thing. Does the hydrogen lamp work? Well, let's check it out. Have you seen the hydrogen lamp?
I've never seen it in my life.
Oh, really? Okay. Well, first off, let's look at the LEDs. The LED, what color light is coming off the LEDs?
White kind of like.
Like yellow.
Yeah, it's white. Some LEDs are more white. Some LEDs are more red, you know, or blue. Some LEDs are more blue, I should say. All right, the situation is when you see all the colors of the rainbow combined, it looks white. So what we have to do is we have to separate the colors of the rainbow. We're going to separate the colors of the rainbow. We could use a prism or we can use a diffraction grating. Essentially, we'll do the same thing. These are diffraction grating glasses. Here, you just take one.
What about these? These are polarized.
The polarized, we aren't going to separate. This is white.
It's like so.
Yeah, I know. I wish I could yellow, but I already grabbed one. Oh my god. Oh, this is not. It's really pretty. It's pretty. It's very distracting. I didn't really like that. See the different colors. Oh god. That's cool, but Christ. Imagine this is what it's like to be on it.
So do you see the spectrum coming off the LED lamps?
Yes.
Do you see all the colors of the rainbow?
Oh, Jesus Christ.
Yeah.
This is for all of them.
Okay. Are there some colors missing?
Yes.
What color is missing from?
No, I see
No, they're all there.
They're all there?
No, we just need Roy G.
Do you see Roy G. Biv in the LEDs? Okay, that's good. Yeah, it depends on the LED. You know, some of them are going to be more faint, less intense than others, you know, depending on the spectrum. But essentially, it's white light and it mimics the sunlight that we get. Yeah, hopefully there's not too much ultraviolet coming off that. Okay. Next, we're going to take a look at the hydrogen lamp. Hydrogen lamp is predicted to give off white light, like the sun. No, not exactly like the sun, but hopefully close enough. And so it's like setting up a little lightning bolt in the hydrogen lamp. Let's take a look at it. Do you see it?
Oh, wow.
Well, what you see is, I don't see white light. Do you see white light? Well, there's some white at the ends, but I should cover that up. It looks pink, doesn't it?
Yeah.
Is pink part of Roy G. Biv?
No,
It's a mixture of colors, right? We have a mixture. Can you tell me what the mixture of colors consists of? Red and blue and some others.
It's mostly,
Mostly red, right?
yeah, with the glasses you can see like the red and the turquoise.
Look through the spectroscope, the blue one. Can you see the?
It's like bluish green. It's like there's two
Okay.
really bright stripes.
Two bright stripes. Okay. Red and green are the
A
brightest.
little bit of indigo, I think.
A little bit of indigo. Well, this is this hydrogen lamp. Do you want to look at the big hydrogen lamp, the sun?
No.
You don't have to look directly at the sun, but you could take your spectroscope and the glasses outside and compare. Yeah.
I don't know how to use it.
You just point it towards.
Like,
Oh, the other way.
oh. Whoa. There's numbers.
Yeah, this measures based on the wavelength. You'll see the numbers there. The wavelengths of visible light range from, it's hard to see. If you want to come up close to the lamp, you can come up to the lamp here and then take a look. Unfortunately, we got a lot of white light bleeding in there. I have to turn off the light.
No, I'm primarily color. I still don't know how to use this. I mean, I'm not seeing exactly what numbers.
There's a square hole on the wide end. Point the square hole to the light source. Do you see lines?
Yeah. Just I see one turquoise and really? Yeah. Point this part. Yeah. This part directly at it.
Yeah.
Yeah.
You'll see it on like really sharp lines.
Yeah.
Then they are. Like a baby blue, red, and purple.
Okay.
Looks like cyberpunk.
Yeah, you gotta. Well, you could. This is the hydrogen lamp. You could compare it to the sun, which is a gigantic hydrogen lamp. If you want to go outside, you don't look directly at the sun, but you just
Look at like the horizon.
look at something. Yeah. Then if you want to go take a look at the sunlight. Did you see something like this? Yeah. Yeah, real big haze.
Almost exactly 400 to 700 nanometers.
Yeah, this is done in terms of wavelength, 400 to let's say 800, 760 is bright. Just around here is the visible spectrum. This is an order of wavelength, which is an order of decreasing energy. So we're going from high energy to low energy here, versus low energy red to high energy violet here. So if we start off with low energy, which has the longest wavelength, this black region is called the infrared, and the sun emits a lot of infrared. You can feel the infrared. This is electromagnetic radiation, so you can feel this like on a cold day. In a cold day, if you stand at the sunshade border, and if you stand in the shade, you're cold, but if you move your hand into the sun, it's warm, right? That's infrared radiation, electromagnetic. And then we go into the red.
Why did the spectrometer only work at 20 degrees deflection from the sun?
Just the angle. Sure. Did you measure the deflection?
Yeah, it was 20 degrees off deflection.
Oh, it's because of this. That's because of where the light comes in.
Oh.
The light only comes in through here. It doesn't come in through here. This is all blocked off. The light comes in here and then it gets separated. And so you always have to hold this at an angle.
Yeah.
Now you point it straight, you don't see anything. You have to adjust the angle.
Oh, 20 degrees.
Yeah, and that makes sense because it's about 20 degrees off. And so we call this a continuous spectrum. A continuous spectrum means all the colors in the rainbow. There are some gaps here. There's a little gap here. Yeah. But overall, we have a continuous spectrum. When you look at the intensity, the most intense part is, do we get much violet? No. It looks like we get mostly what color from the sun? Red. And so the plants use sunlight. And if you look at the leaves, what color are the leaves? Green, the leaves are green, so does that mean the leaves are absorbing green light here? Using them? No. What does it mean if the leaves are green?
Absorbing red.
Yeah, right. They're different things. If something looks green, it could be absorbing all the other colors except for green, and therefore it's going to look green. But there's other ways. There are two other ways that colors can be made. And so let's take a look at that here. So if we write the spectrum, red, orange, yellow, green, blue, and then combine indigo violet, like this, we get the color wheel. Now, do you know the LED lights don't emit all the colors of the rainbow? Do you know what colors the LEDs emit? Red,
blue, and green.
red, blue, and green. Red, green, blue. And so combining different intensities of red, green, and blue can get you all the colors of the rainbow. And so if we have a little bit more red, we shift it maybe to orange. We have a little bit more blue, we shift it the other way. And so red, blue, and green can combine to form the other colors. But what plants use, do you know what plants use? What color light they use? Plants use red, mainly. And so if something is absorbing the red light, so, you know, what does visible light do? Visible light excites electrons. And so electrons in plants, and the chlorophyll in plants, gets excited by red light. And that means it's being absorbed. So if we absorb red light, then the remaining colors add up to, so when we average these colors or add up these colors, they're going to add up or average to green. And so plants will absorb red, which is going to be the most intense part of the solar spectrum, and appear green.
Oh, is that why plants are green, but when you heat stuff up, you don't see green? It's like almost like the opposite.
Yeah, well, this is the kind of the opposite effect. Like, for example, if something appeared violet, what color is it absorbing? If something looks violet, it's not because it's absorbing violet light. It could be because it's absorbing yellow. Or it could be because it's absorbing all colors other than violet. Or it could be absorbing a combination of colors at different intensities, which add up to violet. And so there are multiple ways that things can look different colors. And so when we come back to this, you know, we look at the colors of the hydrogen lamp, and that tells us that it's absorbing or emitting certain colors. And this pink light is a combination of 4 colors. And so when we try to make a lamp using hydrogen, the light coming off this is like this pink violet. And then what we do is we use a visible spectrometer to see what colors make up this pink violet light. And when we do that, we'll just go with this, decreasing wavelength, right, G bib, increasing energy. We see that there are 4. It's hard to see here because there's so much background light. We have a red, and a very specific red. There's a range of reds, you know, from red to red orange. And this very specific red, it gives us a sharp, what we call line here, at a very specific wavelength. And so just one color of red is emitted. And that's the most intense. And then we have a line in the green, which is a little less intense. And then a line in the blue, which is harder to see. The hardest one to see is the violet. the violet because the intensity is very low. And so a lot of people don't even see the violet. But when we combine these four colors, this is what we see to the naked eye. To the naked eye, we see the pink color. But really, that pink color is made up of these four colors in this combination. So this is a discontinuous spectrum versus a continuous spectrum, and that has significant implications. This continuous spectrum means that we can excite the electron to any energy we want. But when we have a discontinuous spectrum like this, what it means is that we can't excite the electron to any energy. In fact, there's black regions here. These black regions are forbidden. Whereas these regions where we see light are allowed. And so this red light is allowed here. This green, but not just any red, it has to be this specific red. And the same thing with the green, blue, and violet. It has to be those specific wavelengths. Otherwise, it's forbidden. So that's a problem because classical physics says that there should be no forbidden. So let's say you're riding a bicycle. You could ride the bicycle at any speed you want, from 0 to however fast you can go. There's no forbidden speed. That's classical physics, and that's what you predict for the electron and hydrogen atom. The electron can move any speed it wants. But when we try to excite the electron, and you can excite it more. We can excite it more and go into UV. We still don't get these. So why is that? And so classical physics failed to predict because classical physics predicted a continuous spectrum. A continuum. But what was observed, it was a discontinuous spectrum. This discontinuous spectrum we call quantized.
Interference.
Quantized, in other words, discontinuous. Yeah, interference with what? What's interfering with the electron?
Maybe some deconstructive interference with the wavelength, with the light.
Well, I mean.
Professor,
Mm-hmm.
is it because electrons occupy orbits, that means that they must jump from one place to the other, and then that specific drop, or
Yeah,
It's
that's what the way the light emitted, right?
there's no in between.
there's no in between, right? There's no in between. In terms of gravitational potential energy, there's an analogy here. A continuum, let's say you're at a ramp here, and you can go to any height that is any potential energy you want. And so there's a continuum of energies available. Versus if you're at a set of stairs. If you're at a set of stairs, then you can't go to any height. You can't go in between the steps because there's no place to stand. And so each step is allowed, but in between the steps is forbidden. So this is what's happening with the electron. So why is that? Not only that, the steps aren't even for the electron because this isn't even. It's not evenly spaced. Well, for ramp versus steps, it's easy to see because, the steps were made. But for an electron, why is it like that? And so let's say electron can move at 10 miles an hour and maybe 25 miles an hour, but it can't move any speed between those 10 and 25. Why is that? And so do you know what quantum mechanics is? I mean, quantum, actually, I should back up a step. Do you know what the theory says? Let me back up there. So there's a hypothesis. The hypothesis you already have, and then the theory came out. The hypothesis was that the electrons orbit around the nucleus. Well, classical physicists said that too. The electrons orbit around the nucleus. The difference is this. There are forbidden orbits and there are allowed orbits. And so that resulted in the Bohr theory. Bohr theory is there are forbidden orbits and there are allowed orbits. And so this first orbit, which we call the n equals 1 for the first orbit, is allowed. And the second orbit, which we'll call n equals 2, is allowed. But we can't have anything in between these two. So for example, if we wanted an orbit of 1.1, just slightly, 10% greater than this, that doesn't happen, or 1.5, or 1.9. We can't have any orbits in between these two. These are all forbidden. Why is that? Well, why that is this is an argument that may not satisfy your curiosity, but why that is because nature behaves that way. So have you ever heard of the postulates of quantum mechanics? A postulate is just, you take it without proof, and so what we say is that this is one of the postulates of quantum mechanics, so that's the way it is. Does that? And this is the way nature behaves, and therefore that's the way it is. But, we'd like to describe it a bit more than that. Is there a staircase in the hydrogen atom or something? Or what's going on? Why are all these orbits forbidden here? Well, anyway, so Bohr, he came up with this. He came up with the idea of orbits. And he came up with, orbits aren't new. He came up with forbidden orbits and allowed orbits. And so the next orbit that's allowed is the n equals 3. And these aren't, at even distances. So the first orbit's here, second orbit, the third orbit's farther out. Fourth orbit's even further out. The fifth orbit's way out here. And the sixth orbit is way out here. This was my orbit from earlier. So we'll do the fifth orbit out here, n equals 5. And then we'll do the sixth orbit out here, n equals 6. How many orbits are there? What's the highest orbit you can have? Do you know what it is? And so way out here, there's an orbit called n equals infinity. Once you hit the n equals infinity, do you know what happened to the electron? Yeah, it's gone. The electron's gone. It's lost. It's broken off the atom. We call it ionized. All right. So what happens is when you excite the hydrogen atom, it can populate these orbits. And so we'll have the electrons occupying these orbits, and what can happen is that they don't stay excited forever. So let's say there's an electron here on the third floor, and it drops to the second floor. That's going to emit red. And so an electron from the third to the second emits red. we call this an electron or electronic transition. So if an electron goes from high energy and drops down to low energy, we get emission. And so it'll emit light. Or if an electron is on the second floor and it gets promoted to the third floor, that would be absorption. So we can use the red photon to absorb it, or we could use electric power or whatever. And so we can absorb. So things can absorb or emit light, and that causes transitions between these floors or these orbits. What if an electron is in the second floor and drops down to the first floor? If an electron's in the second and drops down to the first, it's weird. It looks like it'd be lower energy because it's closer, but it turns out it's higher energy. And so if an electron's in the second and drops down to the first, we emit UV, ultraviolet. And so we can't actually see that. And so we can map these out using orbits, or we can map this out using what's called an energy level diagram. In terms of orbits, the n equals infinity is infinitely far away from the nucleus. Therefore, it's been ionized. In terms of energy, the n equals infinity is not infinitely high up in energy. The n equals infinity, we define this as having an energy equal to 0. And then we'll have n equals 1 down here. Now, n equals, if this is energy 0, this is negative, and the energy is not infinitely far down here. And so it's going to look like something like this, where n equals 1 is like this, n equals 2 has a bigger gap, so it's going to cost more energy. But the further we get away from the nucleus, the less influence the nucleus is going to have on the electron. And so as we go up higher and higher, n equals 4, n equals 5, n equals 6, eventually we have to fit an infinite number of these lines, and they become closer and closer spaced as we go up. And so the red light comes from the n equals 3 to the n equals 2 transition. So 3 to 2, a drop here will emit a red light. The green light comes once we have a 4 to 2 transition. So if we're on the 4th floor and drop to the 2nd floor, then we'll have green light. And then the blue light comes from 5 to 2 transition. And then the violet light comes from a 6 to 2.
Would a different isotope glow a different color?
A different isotope, no,
Would do the same
it
thing?
would be the same color. Because the different isotope would just have a different number of neutrons, and the neutrons aren't going to impact.
Well, I was gonna postulate that, because when you have distance in an orbit, it's affected by the inverse square principle. So I was thinking that the distance from the nucleus and the energy has to be in whole numbers because of the number of protons and electrons. So I was thinking that the orbits in the forbidden zone can't exist because the electron has to be balanced out to a whole number because of the nucleus. Because of the inverse square principle.
Okay.
So I was thinking if there was
Is the inverse square principle doing with gravity?
well, it's anything with distance.
Okay. Yeah, it is. You're right. This is inverse square. In fact, Coulomb's law is inverse square. So as you get further away.
So I was hypothesizing that that's the reason why the orbits are in whole numbers because the nucleus has whole numbers of protons and neutrons. But to test that, I was saying if you have an isotope, would it change the radiation from exciting the electrons? Because you get what I'm saying, to test my theory.
Yeah. Well, hydrogen consists of about 1% H2 deuterium, or no, well, actually less. What is it, 0.0115%? Some small number. But what we say, this spectrometer is very sensitive. And so if there are additional lines from deuterium, we'd be able to see them. And so the deuterium and the hydrogen isotopes are giving the same spectrum here. There's not a separate spectrum for that. And so we should be able to see it. We don't. And so that's saying that having an additional neutron there is not really going to change things.
But if it was there, the intensity would only be 0.15.
Oh, okay.
So you probably won't with the equivalent.
Well, with these handheld ones, we can, but with other ones, you can zoom in. You can blow up the baseline here and zoom in to see if there's another signal due to the other isotope.
I'm gonna test my theory.
No, it's good. It's good to think about these things because that would be better than just a postulate saying take it as is. You know? Well, anyway, what happens if we're on the 7th floor and drop to the 2nd floor? Do you know? Ultraviolet. And so if we're on the n equals 7 and we drop down to the 2nd, then we get UV. 8th to the 2nd, UV. What if we're on the 6th and we drop to the 5th? Then we get infrared. It's a smaller down. And so what this does is this predicts lines that should be observed, not just in the visible spectrum, but also in the infrared and the ultraviolet. Those lines were measured, actually, and there are a bunch of lines in the infrared and the ultraviolet. We see, they give a different spectrum. And so if you just take it, as postulated, the Bohr model says this, or the Bohr theory says that the electrons in an atom orbit around the nucleus. There are allowed orbits and forbidden orbits. Because of this, we're not going to get all the colors of the rainbow. In other words, we're going to get a discontinuous spectrum. This one's called a line spectrum, like this, where each line represents what's allowed. Okay. So once we have the Bohr theory like this, then theory should be able to do what? Predict. And so rather than making a hydrogen lamp, let's make a neon lamp. If you make a neon lamp, does neon lamps give off white light? No. Yeah, it's kind of like yellow, orange, something like that, neon lamp. It doesn't. But using Bohr theory, we should be able to predict, based on the physics of this. But did it work for the neon lamp? No, it didn't. And so Bohr theory failed for all other atoms. So not just neon, but helium, lithium, everything else, it failed. Turns out the postulate's correct. Energy is quantized. That's correct. So Bohr, and classical physics, even though classical physics failed to predict this, classical physics got people to the moon and back. And so classical physics was not abandoned. People still use classical physics. It turns out classical physics is a special case of modern physics. Do you know what modern physics is? It's not Bohr physics. Although, we talk about Bohr because this is the first one. The Bohr model of the atom's wrong. Have you seen this picture of the atom?
Oh, yeah.
Oh, yeah, it's a classic one.
This is not classical because this is still quantum. Is there orbits there? Classical physics just predicts these orbits, but you can have any orbit you want. There's a continuum of orbits, from low energy orbits to high energy orbits. So it's a continuum of orbits. So classical physics predicted a continuum of orbits. Bohr predicted that there are forbidden orbits and allowed orbits. He called this quantized. So, rather than a continuum. Both of these are wrong. Both are wrong. So,
And electrons don't spin.
electrons don't what?
They don't spin.
Spin? Electrons have spin, but electrons don't spin. Electrons are weird. We'll talk about electrons more in detail later. So what's right? Well, or what's our current theory? And so the current theory is quantum theory. But didn't I talk about quantized? Yes, I did talk about quantized. And so Bohr was right in the sense that the electron energies are quantized, but they weren't orbits. And so this is not incorrect. This is correct. When we look at the energy level diagrams, there are forbidden energies and allowed energies. Each line represents an allowed energy. Everything in between the lines is forbidden. And so this would be your stair step type situation. And so for quantum, we have to add a couple of people. So what we do is we take not everything about classical physics is wrong, not everything about Bohr is wrong. And so we take certain components from classical physics, take certain components from Bohr, and we add two more things to this. And so there are two more things that we add. One was from de Broglie, and another from Heisenberg.
Heisenberg made that mistake.
Yes, exactly. Heisenberg is responsible for something called the Heisenberg uncertainty principle. In classical physics, you can predict where the electron is, depending on its energy and where it's orbiting around. In the Bohr model, we can predict where the electron is. If it's in this orbit, we measure it here, and 5 seconds later, where is it going to be? Well, we can predict it because it's following a predictable path. But in quantum theory, we can't predict it. In other words, we describe everything in terms of the uncertainty principle means we describe everything in terms of probability. So rather than predicting, let's say, the position of the electron, we'll just come up with a region of space where we're likely to find that electron. So,
Doesn't that apply to the photon? Or the double split experiment? Because you can't predict where the photon is going to be.
okay. Yeah,
But the electron, it doesn't apply to the electron.
it does. It does apply to the electron, oddly enough. That's from de Broglie here. De Broglie stated something called wave particle duality. And so there's a famous experiment called the double slit experiment. If you have a wave, it could go through, if you have two slits like this, although double slit experiment, you don't need to know this for Chem 4. Let's say you have an ocean wave coming. You have an ocean wave coming, it can go through both slits. And then you'll see the wave coming out this slit, and you'll see the wave coming out this slit, right? And so waves can go through both slits here and here. Electron, can it go through both slits? Electron should go through one slit or the other slit, right? Particle. But electrons have, even though we think of electrons as being particles, they also have wave properties. And so oddly enough, you know, if you put a detector here, you can measure if the electron goes through this slit. If you put a detector here, you can measure it if it goes through this slit. But in reality, what happens is electron goes through two slits, and so it has this wave pattern here that you can see. This wave pattern that we see is the interference between these two waves will create a pattern in itself when these two waves combine.
What if that's not an electron? It's an electric field until you measure it and it collapses.
If it's an electric field going through what, both slits? I don't know. I haven't thought about that. Electric field.
Not actually an electron yet.
Yeah. Well, electric field a moving electric field, like light, oscillating electric field. Yeah, light is going to have the same. Normally when we think about light, we think of waves, transmission of energy. But light can have particle-like properties. And so you can actually measure certain things, like particles, where it may go. But before I get into this, let's just talk about what impact this has on this. We have to talk about interference. So if we have let's say we have two waves, and we combine them like this. So if we have two waves like that and combine it, if the peaks line up and the troughs line up, then we call this constructive interference. And so this is going to look like this. But if there's a mismatch, that is, it can be the slightest mismatch. It doesn't have to be a perfect mismatch, but I'll make a perfect mismatch. So in this case, this peak lines up with this valley or trough. This peak here lines up with this valley, vice versa. We end up with nothing here. Basically, these two waves cancel each other out. And so here they are additive. This is constructive interference. Here, this is destructive interference. And so in terms of de Broglie, our visualization of the atom is different. If the electron is behaving like a wave and a particle, then what we have to do is we have to account for this oscillating behavior, the wave. And so if the electron starts off here and then kind of oscillates like this and then ends up here, then this pattern can just be repeated. And this would be constructive interference, or it just follows the same path. if I increase the energy of that electron just a little bit, and so I just increase it a little bit, what can happen is they can be off a little bit. And if they're off a little bit, then eventually what's going to happen is they're going to cancel out. And so this ends up at 0. So this would be allowed where we have constructive. This would be forbidden where it's destructive. And so this energy, which is just slightly higher, shorter wavelength, is destructive. And so we have to have it like that. It's easier to see in terms of standing waves. These are one-dimensional standing waves. This would be like a string on a musical instrument. There are forbidden tones and allowed, or forbidden frequencies and allowed frequencies. And so this would be allowed here. But if I increase the wavelength or decrease the wavelength a little bit, it would be forbidden, because it wouldn't be able to attach there. And so these would be forbidden. And the purple would be allowed.
So what is this, like a quantum harmonics?
Yeah. Right. The next allowed one would have something like this. See? And so when we go, this would be one cycle here, one full wavelength. This would be 1/2 wavelength. And so 1 times 1/2 wavelength is allowed. And then we got 2 half wavelengths here. And we could have 3 half wavelengths here. So we could have n equals 1, n equals 2, n equals 3 here. But we can't have n equals 1.1 because 1.1 would be a little too long, or 0.9, which would be a little too short. And so the only one that would be allowed is n equals 1. And so what we can see is we'll see quantized energy levels for a string where only certain energies for the string are allowed, the other energies are forbidden. And so we can take a look at a little video illustrating this.
So what we have here is the frequency generator. It's connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, it sends away. It sends away down to this end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me turn this on. Well, so it's sending waves back and forth, but these waves are out of sync, if you like. They're not exhibiting consistently constructive or destructive interference at any one point. constructively interferes with the next wave that comes down right at this point. Now the waves that reflect, that come down and reflect, destructively interfere with the incoming waves right here. And that's called a node. I can touch it and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera. So here we have what's called the second harmonic. It's the second possibility for a standing wave for a string that's held at both ends. Because notice, this is a node, this is a node, and the middle is a node. So we have three nodes for this one. Now, like I said, second harmonic, well, what's the first one? The first one will be half this number, so 8.5. And there we go. It's basically the scenario of a jump. Now, I can find any of the other, or all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5, I guess that was 25.5. And there we go. So that's the third harmonic. How many wavelengths is this? Well, it's 1 and a half. 1 and 1/2 wavelengths. And it's easier to see in high speed. So check out this shot with a high-speed camera and verify for yourself that it is 1 and 1/2 wavelengths. So again, third harmonic, 1.5 wavelengths. Well, let's go to the sixth harmonic. The sixth harmonic will just be double this frequency. So we go up to 50. And there we go. That's the sixth harmonic. Beautiful. And it's 6 times the fundamental frequency, which we mentioned in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through the calculations and the derivation.
So this would be the first harmonic. It would be just 1 times 1/2 lambda. Lambda is the wavelength. The second one would be 2 half wavelengths. The third one would be 3 half wavelengths, or 1.5 wavelengths, and so on. All the other energies would be forbidden. And so as he's cycling and jumping up, it just jumps up to the next available, next available. And so we're going to have allowed and forbidden states. This is one-dimensional. Let's take a look at two-dimensional. Now, the two-dimensional waves are going to be more intricate. And so this is going to cycle through energies. So this is forbidden, 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 until it comes to an allowed. This would be an allowed. And so we have a wave here. Go like up, and then here down, and then back up. This is called a node, where the wave amplitude goes to 0. So this kind of forbidden, forbidden, and then that's allowed there. Forbidden, and then allowed. Another one. You can see a lot more complex wave patterns in there. And these plates, these metal plates can only vibrate at certain frequencies. There's certain frequencies called the resonant frequencies for the plate. The resonant frequency for the plate is going to depend on how thick it is and how big it is. You know? And the same thing with this. It depends on how long this is and whatnot. So we have something for this here. But anyway, let's take a break right now, and then we'll talk more about this after the break.